Hi again, this is Mrs. Bookman. I'm here to talk to you about more things that you can do with polar complex numbers, which is DeMoivre's theorem. Okay, so let's get started. Normally, if we were in class, we would spend some time discovering and things like that, but for this video, I'm just kind of told you the rules and tell you how to do it. So consider this. Let's say we had a complex number. Of course, we have an a plus a bi, and I asked you to raise it to the seventh power. Nobody wants to do that. That means you would have to sit down and do 3 minus 2i 7 times, double distribute a zillion times, and that would take a long time. So one thing that we can do is we can actually do this rather quickly by using polars. So we have some examples. Now, obviously, if you have something to the first power or to the second power, it doesn't take that long to go ahead and multiply it out. So you would maybe not want to use polars. But as soon as you start getting into something cubed or to the fourth or anything higher, then it is actually way faster to use polars. So what you're going to do is the first thing is I want you to recognize that these are in rectangular because you have an a plus bi. And you first always have to find r, and you always have to find theta. How do you find r again? A squared plus b squared square rooted. And how do you find theta? You do inverse tangent, and you have to remember what quadrant you're in, okay? And then you're going to write it like the last video I had for you, where you write it as a polar number. Once you have it as a polar number, you'll be able to use DeMoivre's theorem, and then at the end, you're going to want to convert it back to a complex number. Because remember, we're just using polar to do something that we know how to do in rectangular. Okay, so when you raise it to a power, this is the general rule. You find the radius and then you raise it to that number. So if it's cubed, you do raise it to the third power and so forth. And then you take that angle and you multiply by whatever n is. So let me walk you through an example. We have something here in polar. N is being to the ninth. It would take us forever to actually sit down and multiply that out. So I'm going to use polar to answer this question really fast. I'm first going to find r by doing a squared plus b squared square rooted. And so I get r is 2. And then at the same time, I'm going to find my theta. Now I'm in quadrant 4 because this is positive, x is positive, y, the imaginary x-axis is negative. And I'm going to do negative 1 over root 3. And so that's going to be 11 pi over 6. Okay? So then what I'm going to do is I'm going to use that rule where I say take r and raise it to that power. So I'm going to do 2 to the ninth equal to the cosine of n, which is 9 in this situation, times my angle plus I sine 9 times 11 pi over 6. That actually gives me 99 pi over 6. But if I want to reduce it, that's actually 33 pi over 2. Now, the hard part is you want to figure out what 33 pi over 2 is actually in relation to. So I did a little simplifying. First, I did 2 to the ninth, which is 512. And then I figured out 33 pi over 2 is the same thing as going around and around and around and around and around and around. And it's the same thing as pi halves. From here, now I'm not leaving it in polar because I actually want to figure out what this would be if I sat down and did that 9 times. I then just figure out what is the cosine of pi over 2 and what is the sine of the pi over 2, which is 0 and 1. And so voila, your answer is 512i. So if you were to sit there and do this 9 times out and hopefully not do any algebra mistakes, you would end up with everything canceling out except for 512i. So it's pretty cool. You're using polar intermixedly to do something super fast. Okay, so if you want to pause the video and practice a couple other ones, that's great. At the end, you can go back to the document and I linked my work and answers for the rest of them, but I'm going to keep going with going the other way. So one of the things is we could raise it to a number, but we also could do a root. So these are the roots of complex numbers, which is similar but different, okay? So if you want to find the roots, again, in class, we would have made you look at this and study this chart. And so if you want to pause the video and kind of study it, that's fine. But first thing I want to point out is if you have a cubed root, you have 3 answers, 3 roots. If you have a 4th root, you have 4 answers. If you have a 5th root, you have 5 answers, and so on and so forth. So Again, the first thing I have to find is this is something in rectangular. You need to first find r by doing x squared plus y squared, and you also need to find theta. And theta should be in terms of what quadrant you're in based on if x and y are positive or negative. Okay, so what actually happens is it is way easier. I know we've been preaching radian, but it is impossible. You actually want to do this in terms of degrees, because roots are evenly spaced apart. Okay, so this DeMoivre's theorem is actually for finding the first root. So what we're going to do is similarly is in the other one, we took r raised to that power. If we're doing roots, we're going to actually take r, the nth root of that. So if we're doing cube roots, we would do cube roots. If we're doing fourth roots, you would do the fourth root of r. Okay, and instead of multiplying n times theta, we're actually going to take theta divided by n. So notice up here, when we had 120 and you were doing the cube root, we took 120 and divided it by 3 to end up with 40. We took 300 and divided it by 4 to end up with 75. We took 90 and divided it by 5 to end up with 18. Okay, so this gives you the first root only. Okay, so if you want to find the other roots, and here's where we're lazy. In math, we like to formally write out the first one with the r and the angle. But then we're saying, okay, we're going to insert these other angles, and those are where the other ones are. Okay, so we're kind of lazy, and you can just kind of put it on the side where the other roots would occur at. So to find the other angles, if they're evenly spaced apart, you take the full circle, which is 360 degrees, and you divide by how many you need. Okay, so if I divide by 3, that means the other roots are 120 degrees apart. So take 140 and add 120, you get 160, add 120, you get 280. If you added 120 again, you'd actually be over the circle, so you're done. Okay, so if you have the fourth roots, you would take 360 and divide by 4, which would mean that they're 90 degrees apart. And so I added 90 and added 90, added 90. Okay, so I'm going to walk you through one, and then the rest of the answers can be found on the worksheet. Again, start with finding r, finding theta. Okay, so I found r and I found theta. This time, instead of using radians, I really want to use degrees. Okay, so to find the first, I'm going to take the cube root of 2, and I'm doing cube roots because I'm doing cube roots, not fifth roots. Cube root of r, and I'm going to take 120 divided by 3. So my first answer is at 40. So I'm formally going to write the first answer. And then I'm going to write the other two angles occur at 160 and 280. How did I get those? Because if I'm doing cube roots and they're evenly spaced apart, I have to add 120 and then add 120 again. Okay, so check out the rest of these and the answer key and let us know if you have any questions. Otherwise, you're good to start your Math Excel homework, and that is the last lesson in polars.